Welcome everyone, my name is Marco Dozza and today I will talk about automation levels. Have you ever been a passenger of a vehicle that drove by itself? And would you ever consider traveling in an automated vehicle knowing that you will be exposed to a situation that will scare you? I guess for most of you the answers should be yes and yes. Undergrounds, airports, mines and amusement parks often use driverless vehicles, and the chance that you have experienced this is pretty high. So what's so different with automated cars then? In this lecture, you will hear about the SAE taxonomy for automation levels and discover that the operational design domain and the complexity of the object and event detection and response task are much more challenging for automated cars than for the examples in this slide. If this sounds a bit awkward to you, do not worry, we will get back to this in the end of the lecture. As for now, in this lecture, we will start by understanding the motivation for automated driving. We will then define automation levels by familiarizing with some key concepts from the SAE taxonomy. Finally, we will discuss some of the current challenges for automated driving. In this slide, I just listed for you the learning objective of this lecture. You may now pause to let this information sink in, or use these slides once you watch the full clip to check if you missed anything important. So, why do we want for our vehicles to drive by themselves? Well, there are several opportunities with automated driving that make it very appealing for several stakeholders. On the one hand, machines are not impaired by alcohol, fatigue, or distraction, and promise to make our road safer. This is, of course, a big statement, and we will discuss this aspect a bit further before the end of this lecture when we will talk about Level 3 automation. Automated driving also promises to reduce congestion by optimizing the use of current road infrastructure. For people with disabilities, automated driving may create new opportunities for personal mobility. Automated driving will also relieve the drivers from a cognitive demanding task. Finally, as drivers become passengers, they will have more time to do what they want, reading a newspaper or do some work on their laptops. For these reasons, automated driving is expected to revolutionize transport in the near future. Automated vehicles are easy to imagine, but hard to develop and understand. The automation levels help us understanding what automation is supposed to do by defining how the driving task is split between the humans and the machines, and what machines are capable of. Several institutions have proposed different automation levels, and I refer to them in the references. However, today, everybody seems to have agreed on the levels of automation proposed by SAE, so we will stick to the SAE taxonomy. By the way, SAE, or more correctly SAE International, is an association concerned with standardization within automotive engineering, which was also formerly known as the Society of Automotive Engineers. These SAE levels of automation explain how the driving task moves from the human to the machine in 5 steps, starting from a level 0 or L0, where the human is totally in charge, pretty much what we have today, to an ideal level 5 or L5, where the machine is able to take full control and responsibility of the driving task in any situation. Before we define each automation level, let's familiarize with a few concepts that may help us appreciate the difference between these levels. The first term we need to get acquainted with is dynamic driving task. The DDT includes everything you do as a driver at the operational level and tactical level as defined by Michon in his 1985 paper. If you are not familiar with this paper, please take a look at the references. Shortly, the DDT includes tasks such as steering and braking, deciding to overtake or to perform other maneuvers, but it would not include strategic decisions as route planning. An important component of the DDT is the object and event detection and response. As you drive, you monitor the environment, identify obstacles and other road users, and control the vehicle accordingly in the lateral and longitudinal direction to keep your driving safe and legal. That is object and event detection and response. We will see that humans and vehicles may split the DDT and the OEDR, and this split may help us define the automation level. For instance, an active safety system, such as Adaptive Cruise Control or ACC, may be able to brake and accelerate to keep a constant speed or a constant gap to the vehicle ahead. ACC would undoubtedly contribute to the DDT and therefore contribute to automatizing the driving task. This is a representation from SAE about the driving task, including the DDT and the OEDR. It is important to notice that the lateral and longitudinal control that we have already defined in a previous lecture are not included in the OEDR, but are part of the DDT. Soon we will see how this part of the DDT will help us define the difference between L1 and L2. As for now, going back to the ACC example, ACC is able to take responsibility for the longitudinal vehicle control in the DDT, but not for the OEDR. Functions such as ACC, actually according to SAE taxonomy we should call ACC a feature and not a function, do not work everywhere and at any time. For instance, the first ACCs did not work at speed lower than 30 km per hour, and current ACC still have a limited operational design domain, meaning there are situations in which, because of sensor limitation or for other reasons, ACC may not be available. The set of situations in which ACC is expected to work define its operational design domain, or ODD. A consequence of having a specific operational design domain is that we cannot be sure to be always within the ODD during driving, and therefore, during our trip, we may end up into situations that exceed the ODD. In such case, we need a fallback to continue driving or to minimize the risk of that situation. A fallback may also be needed in case of a system failure. If reestablishing the full operation of the vehicle is not possible, the minimum requirement for a fallback is to reach a minimal risk condition, such as slowing down and stopping the vehicle in a safe place. As an example, our ACC may exceed its ODD because the deceleration required to cope with the vehicle suddenly braking in front of us is higher than what ACC was designed for. In this case, ACC would provide a warning to trigger a fallback, the driver taking control of the vehicle. We will see that the concept of fallback helps us understanding the difference between L3 and L4+, and the concept of ODD to tell apart L4 from L5. Okay, why don't you take a break now and look at the self-assessment questions?